This lesson is part 1 of section 10.5 on parametric equations. We have two main objectives for today. We're going to sketch curves that are represented by sets of parametric equations, and we're going to do that in a couple different ways. We're going to use tables to graph our parametric equations, and we're also going to use our calculator. But our other method that we're going to rely on is eliminating a parameter so that we can rewrite the equation as a singular rectangular equation and then graph from there. So our second objective actually relates to our first objective as well. So let's talk about what a parametric equation even is. So a parametric equation is a system of equations with more than one dependent variable. Often parametric equations are used to represent the position of a moving point. And this is a really important concept for today. To help you kind of grasp this idea, I want you to imagine that you're on a Ferris wheel. I think this is a really relatable example because you've either been on a Ferris wheel before or you know how one works. So let's imagine that you're riding on a Ferris wheel that has a 35-foot radius and whose lowest point off the ground is 5 feet. So let's show that that segment here is 5 feet. Now it completes one clockwise rotation every 12 seconds. So here that arrow is showing the general direction of motion here. And it completes a rotation every 12 seconds, so we're definitely dealing with some periodic functions. Now your x and your y position both depend on time. So no longer do we have x as the independent variable. Now your x and your y both depend on the variable time. So time is now your independent variable. Okay, and a lot of times we're going to use time as our independent variable. It doesn't always have to be, but in our book I think it uses time pretty much exclusively. Now we call time the parameter. So the parameter is the variable that relates both equations. So it's relating the x and the y position in terms of time. Now using our example here, I got a table that shows your position at certain times. Now at time equals 0, this is represented here. At time is 0, my x position is 35 feet and my y position is 40 feet. So we're using here these as the axes. So here's my x and y axis. And at this point, time is 0, we have an x position of 35 and a y position of 40. Now after 3 seconds, I'm down, so after 3 seconds of this clockwise rotation, I'm now here at this point. So when time is 3, now I have an x position of 0, since this is the origin here, so x is 0, and my y value is positive 5, okay, since it's 5 feet off the ground. Now I'll go another 3 seconds. So now I'm at time is 6, excuse me. And now my xy position is shown with negative 35, that's my x position, and positive 40 in my y. So that's my vertical, my horizontal, and my vertical position. If I go to time equals 9, so after 9 seconds, now my horizontal position is back to 0, and my vertical position is up to 75, right? Because it would be 35 plus this 5 feet off the ground. And then finally, after one full rotation, I am back, so at time is 0, and at 12 seconds, I'm back to my original position, 35, 40. Now this particular cosine function actually models the x position for any time t on that Ferris wheel. So we have 35 times the cosine of pi over 6t. Now if I asked you to graph that, you would set pi over 6t between 0 and 2 pi, and then you would solve for t. So we'd end up with a period of 12. We'd cut that up into 4 different intervals here, and then we would graph that cosine function. So that's just a little bit of review. But we can also express the y position for any time t on that Ferris wheel using a sine function, negative 35 times the sine of pi over 6t plus 40. So we say that x of t and y of t are parametric equations. So these describe your position on the Ferris wheel for any time t. T is your independent variable, and we end up with a position xy. So I'm hoping that after we go through that Ferris wheel example, after seeing a real-life application, you'll have a better grasp of what parametric equations are. Now below here I have the formal definitions that are given in your textbook, so you're more than welcome to read through these, but I just want to highlight a couple points. Remember that your variable, your independent variable, is called the parameter. Now oftentimes it's t, and in our textbook I think they exclusively use t, but that's the independent variable for both of your parametric equations. So if we have x equals f of t and y equals g of t, notice that both x and y are in terms of t. So these are functions of t, the independent variable there. Parametric equations also have a definite direction of motion, which the book calls the orientation of the curve. Now in this Ferris wheel example, that direction of motion, or the orientation, is clockwise. Okay, so this is how we would show the orientation or the direction of motion of that curve. All right, let's start with our first parametric curve. We are going to graph the following set of parametric equations: x equals t squared plus t and y equals 2t minus 1. Now our first method is going to be graphing using a table. Now as you can see, I already set up a table for us. Okay, so here are the t values that we're going to use. So all we have to do is select values of t and plug them into each parametric equation, and then we'll plot our points, our xy points. So when t is -2, x is going to equal 2. And that's because x is defined to be t squared plus t. So if I take -2 and I square that and I add -2, I end up with 2. Now y is going to equal -5, and that's because y is defined to be 2t minus 1. So 2 times -2 minus 1 gives me -5. So this is my first xy position, 2, -5 when time is -2. So as you can see, using a table is pretty straightforward. All you have to do is select values of t and then plug them into each parametric equation so that you can get your x, y position. So I'm just going to fill out the rest of this table and pause the video. All right, so there's our table all filled out, and now we're going to go ahead and actually graph this parametric curve. Now when I graph this parametric curve, I start with a normal xy axis. Okay, I plot these points just as I normally would when I have an x comma y pair. So I'm going to graph our first point. When time is -2, I'm at a position, an xy position, 2, -5. So if I graph 2, -5, this is just a rough sketch, so let's place that about right here. This is when time is equal to -2. So I'm just going to label this time equals -2. I have the coordinate 2, -5. Now when time is -1, I have a new xy position, 0, -3. So now I'm at 0, -3 here. And this is for time equaling -1. Now I'm just labeling these times because what we're going to later do is label the direction of motion here. So as you can see, as t increases, our points are plotted from here. We started here, and now our position moves to here. So that's definitely showing you a direction of motion, which we'll label after we plot all of our points. Now when t is equal to -1/2, we have the coordinate -1/4, -2. So let's see if that's -1. -1/4 is about here, so let's put that about right there. So this is just a sketch. I know it's not completely accurate, but I'm going to label this now with t equals -1/2. Okay. Now our next coordinate, when t is 0, is the coordinate 0, -1. So our position now is 0, -1 when time is equal to 0. All right, now when time is equal to 1, we have the coordinate 2, 1. So now I have this coordinate right here, and that's when time is equal to 1. So as you can see, when I connect these coordinates, and I just showed you this specific set of values. We could have graphed a lot more, and I'll talk about that in just a second, but when we connect these points here with a smooth curve, I want to show that the direction of motion here is in this direction. So as t increased, we plotted our points and it followed this direction of motion here, or the orientation of this particular curve. Now, of course, we could have plotted more points. So you might be asking, well, how do I know which points to plot? And the reason I picked this set of points here is because I knew that this was going to be a parabola that opened to the right, and that specific t value, -1/2, gave me the vertex, -1/4, -2, for this particular parabola. So the question is, how do you know which points you're supposed to plot? And the answer is you don't really know ever. You just have to pick enough points to be able to plot and get a general shape of the curve. So this is why graphing using a table isn't the best method. It works, but it's, kind of a shot in the dark. Like, are you getting the right coordinates? So we're going to show you another method in just a second, but we'll continue now with this whole graphing using a table idea. So this is the final graph right here for that parametric curve. Okay, in example 2, we're going to sketch another parametric curve. This time it's defined by parametric equations, x equals t squared minus 2 and y equals 3t. Now this time they also give us a specific interval for our t values from -2 to 2. So as you can see, the table here reflects those particular t values. Now when we actually graph this parametric curve, it's going to look slightly different than number 1, but I want you to fill out this table, so I want you to pause the video and fill out the table on your own. I'm going to do the same. Just remember, you're plugging in values of t to find your x and your y position. So I'd plug in -2 here, and then I'd plug in -2 here to find my x and y position. So go ahead, pause the video, and fill out the rest of the table. Okay, so there's the table filled out, and now I'm going to plot these points using a normal xy axis. Okay, so I've got coordinates 2, -6. Let's just pretend that's down at -6, and that's when time is equal to -2. When time is equal to -1, I have the coordinate -1, 3. No, I'm sorry, -1, -3, so about right there. And that's when time is equal to -1. So as you can see, the direction of motion here is similar to the last one. So there's our first xy position, and now here's our second, so it's moving for sure in this direction here. When time is equal to 0, I have the coordinate -2, 0. So let's put that right here. And when time is equal to 1, I have the coordinate -1, 3. So we'll put that coordinate about here. When time is equal to 2, I have the coordinate 2, 6. So let's put that about right here. Okay, so as you can see here, I have another parabola that's opening to the right. And this time when I do the direction of motion, I'm not going to show that these points would continue past here at all. Okay, so I'm just going to connect between the coordinates that I've plotted here. And when I show that direction of motion, I still use those arrowheads. But I don't go past these 2 points here from time is -2 to time equals 2. So that's the graph here for this particular parametric curve. So in our previous 2 examples, we graphed the parametric curves by using a table. Now I'm going to show you an alternate method, which is graphing by eliminating the parameter. So we're actually using the exact same example as number 2 above, but this time we're going to eliminate the parameter. Now remember, the parameter is the independent variable in your parametric equations. So we want to eliminate the t in one of these equations. So to do that, you're going to solve for t, and then you're going to make a substitution back into the other equation so that you can eliminate t. So I'm going to do this 2 different ways because you could solve for t in either this parametric equation or this one. So I'm going to do both just to show that it doesn't matter which one you choose. So I'm going to begin here first by solving for t in x equals t squared minus 2. So to isolate that t, I need to first move that 2 to the other side, and then I'm going to take the square root of both sides. So I end up with positive or negative root x plus 2 equaling t. Now I'm going to substitute this value here, the t, into the other parametric equation so that I can get rid of that t. Now I end up with y equals 3 times positive or negative root x plus 2. Right? That's the t value here, which is going to simplify to either positive or negative 3 times the square root of x plus 2. So as you can see, you've just created what we call a rectangular equation. A rectangular equation is what you're used to and what you've graphed up to this point in your math career. So we've taken 2 separate parametric equations and eliminated the parameters so that we can create one rectangular equation. Now, alternatively, we could have chosen to isolate the t here. Usually you go with whatever one is easier to isolate. So here, if I isolate the t, I end up with y over 3 equals t. Now I'm going to make the substitution here into the other parametric equation. So now I have x equaling y over 3 squared minus 2. So I end up with x equaling y squared over 9 minus 2. Now these 2 equations, okay, are equivalent to one another. Obviously here y is a function of x and here x is a function of y. But both would end up giving me the exact same graph as the one you've seen up here. Okay, so we would definitely get this exact same graph. Now when you find your specific points though to graph, because remember this is from -2 to 2 in your for your t interval here, you need to find the corresponding x values or the corresponding y values for whichever one you decide to use. Okay, so if you, for example, decided to use this particular equation, I need to know the specific y values that I would be plotting here. Okay, so that means I'm going to use from -2 to 2, I'd find that y is equal to -6 and y is equal to, when t is 2, +6. So between here is what I would be plugging into that particular, it's not really a function, it's a relation, but that's what I would be plugging into this particular y value, okay? Now, the direction of motion is not as easy to see when you do a parametric curve by eliminating the parameter because you don't get the specific points that we saw here, right? When we plotted specific points, you can clearly see a direction of motion. So when you eliminate the parameter, in order to get that direction of motion, you're going to have to plot a couple of different points. So you're just going to have to see how it moves from one point to the next by plugging in specific values. Now, I'm not going to sketch this curve just because I know it's going to look exactly the same as this one. So we're going to just move on now and use our calculator. There's a little note here at the bottom that says that eliminating the parameter is not always easy, okay, and in some cases it's not even possible. Now in those cases you would have to set up a table to graph, okay? So I don't think we give you any problems where you can't eliminate the parameter, but just know that it doesn't always work to eliminate the parameter. But for me it's the easier method because you can graph this, I think, much faster, or even this parabola that opens to the right. You can graph those much faster than you would, you know, by plotting points. Okay, so let's move on now to graphing on your calculator. All right, now using our calculator, we're going to graph the exact same parametric curve as examples 2 and 3. So you probably recognize this problem again, but when you graph this on your calculator, I think it's cool that you can always just check to see if you've graphed stuff right on your homework. What you need to do though is change your mode. So if I go to mode, instead of being in function mode, I want to go down and scroll over to parametric mode. Now when I go to my y equals, now I see x1 and y1, so I have two different entries for my parametric curves here. Now I've already typed in our variable t. Now to type in t, you don't have to hit like alpha t or anything. You're actually just going to hit our variable button right next to that xt theta n here. If you just type t, you get a t. So now I'm going to square that and then subtract 2. So I have t squared minus 2, that's what x is equal to, and y is defined as 3t, so 3 times t. Now when we graph this, we're going to just hit zoom 6 real quick. I just want to make sure you're in a standard window at first. Now if you look at this curve that we're getting, that definitely doesn't look like the curve that we got in our problem. Now if you go to your window, that's because the standard window starts from 0 and it has a t max of 2 pi. So it goes from 0 to 6 here. 2 pi is 6.28. So that's because a lot of times in parametric equations we're dealing with cosine and sine functions, which we'll get to in just a second. So that's what your standard window looks like. So I'm going to adjust this now to be from -2 to 2. And when it says t step, that means the increments of t. Now, you don't have to make t so small, the t step here, that's 0.13, so it's calculating every value between -2 to 2 in steps of 0.13. That's really tiny. We can change that to 1. So if you model it just like the picture here in the notes, you should be fine now. If I go to graph this, now I see that curve exactly the way we graphed that, okay? So that's how you can use your calculator then to graph any parametric curve. All right, now in examples 5 and 6, we're going to deal with parametric equations that are defined by cosine and sine functions. When you see parametric equations with cosine and sine functions, you definitely want to eliminate the parameter, because trying to plug in values between 0 and 2 pi here for t and plotting points and using a table would take a long time. So instead, we're going to eliminate the parameter. So remember, when you eliminate the parameter, you're trying to isolate t in one equation so that you can make a substitution into the other. Now in this case, if I try to isolate t, I would have x over 5 equals the cosine of t, and then I would take the inverse cosine of x over 5 to isolate t. Now then I would make that substitution over here, so I'd have y equals 2 times the sine of the inverse cosine of x over 5. Now obviously we got rid of t, we eliminated the parameter, but this is definitely not easier to graph than the two original parametric equations. So this is not going to be how I eliminate that parameter. Instead, I'm going to rely on a really useful trig identity. Remember, cosine squared t plus sine squared t is equal to 1. Now, if I go back to my original parametric equations here and I isolate the cosine of t, I have x over 5 is equal to the cosine of t, and I have y over 2 is equal to the sine of t. Now, by making the substitutions in here, I end up with, so cosine of t is equal to x over 5, right? So if I make that substitution here, I have x over 5 squared plus y over 2 squared equals 1. Now I hope you're recognizing this as the equation for an ellipse. So we have x squared over 25 plus y squared over 4 equals 1. Now that's probably the form that you would have recognized from 90s, Algebra 90s, when you graphed ellipses and other conic sections last year. But basically and just to review, when you graph this ellipse, this is going to be elongated in the x direction because our a squared value here is larger. So we're going to go out 5 units from the origin. This is that distance A, and 5 units out here. Okay, so those represent the vertices of your ellipse in the x direction. The vertices for your ellipse in the y direction are defined here by the b value, which is 2. So we're going to go up 2 units here. So this is b, 2 units, and down 2 units. And maybe we should have made this a little bit bigger so it's not so tiny. But this is the ellipse. Now we have to also indicate a direction of motion, okay? So always make sure you're indicating that direction of motion. So remember that when you eliminate the parameter to graph a parametric curve, you actually can't tell what the direction of motion is. So you need to at least plot a couple points so that you can see how that motion is indicated, okay? So if I let t equal 0, so at time is 0, I end up with x equaling 5 times the cosine of 0 and y equaling 2 times the sine of 0. So if I just evaluate here, I have 5 times the cosine of 0 is 1, so 5 times 1 is 5. And here, sine of 0 is 0, so 2 times 0 gives me 0. That means that my first point here, 5, 0, when time is equal to 0, is right there. Okay, that vertex of one of the vertices of your ellipse. Now, if I let, I want to know, as time increases, what the direction of motion is. So I'm going to let time equal pi over 2. Okay, so I'm just going to go to another increment. I can make that pi over 6. I can make it anything I want, but I'm going to do pi over 2 because those values are usually pretty easy. So now if I evaluate the cosine of pi over 2 and the sine of pi over 2, well, the cosine of pi over 2 is 0, so I have 5 times 0, so I have 0 here. And 2 times the sine of pi over 2, which is 1, gives me 2. So I now have the coordinate 0, 2. So that gives me this point here. So when time is equal to pi over 2, I'm at 0, 2. So as you can see, the direction of motion here is counterclockwise. So I'm just going to indicate that here with some arrows. All right, lastly, in number 6, we're going to sketch the parametric curve, which is defined by parametric equations. X equals 6 times the sine of t, and y equals 3 times the cosine of t. Again, we're going to use our identity. Cosine squared t plus sine squared t is equal to 1. So we can eliminate the parameter here if we isolate the sine of t and we isolate the cosine of t, and we make our substitution into our identity. So we have x over 6 squared, so this is really sine squared, plus y over 3 squared equaling 1. And again, we have another ellipse. So we have x squared over 36 plus y squared over 9 equals 1. And again, your a value here is going to be 6, and your b value here is going to be 3. So again, I have an ellipse that's elongated over in the x direction here. So I have 1, 2, 3, 4, 5, 6. So here are my vertices, and then my co-vertices are at 3 and 0, negative 3. All right, so there's my ellipse. Now again, I want to make sure I have the direction of motion also graphed here. So I'm going to plot a couple points. So I'm going to let t equal 0 first. When t is equal to 0, I have x equaling 6 times the sine of 0 and y equaling 3 times the cosine of 0. So I've got x equaling 6 times 0, so 0, and y equaling 3 times 1, so 3. So my first point that I'm plotting then when time is equal to 0 is the point 0, 3. So the point 0, 3 is here, so this is t equals 0. Now at t equaling pi over 2, now I have x equaling 6 times the sine of pi over 2 and y equaling 3 times the cosine of pi over 2. So here I have 6 times 1, so x is 6, and here 3 times 0, so y is 0. So I have the coordinate 6, 0. So when time is equal to pi over 2, then I have the coordinate 6, 0. Okay, so I'm at one of my vertices of the ellipse. So as you can see, the direction of motion this time is clockwise. Okay, so as we increase in our t values, now the direction of motion is in a clockwise direction. All right, that is the end of the lesson. Tomorrow we're going to get some more practice with some more difficult parametric curves, and we'll see you tomorrow in class. Nice job. Bye-bye.